Hello, good morning, guys. I hope that you are doing well today, and I hope that you can hear me. So, on the screen right now, what you can see is the beginning of our new lesson today, which is based on the three-wire distribution system. So, today's plan is first, we are going to do the three-wire distribution system, and we are going to see how the voltage and how the currents are going to interact between each other whenever we have an additive polarity, like in the case of having two power sources, like we can see that we have on this simulation. In spite of being able to see the two-wire distribution system, which is what we have in our homes, right? We have line one, line two, and then we have a neutral conductor, which is also called the identified conductor or the grounded conductor. Okay, so now what we are going to do, we are going to see the behavior of the circuits when we have a balanced load, and also what's going to be the behavior of the circuit when we have an unbalanced load. And when we have an unbalanced load, we are going to see also how much of the unbalanced load is going to go through the neutral conductor. That also, because we don't have perfect balanced load, is called the identified conductor. In spite of doing that, also, we are going to see that the reason why we need not only 120, but also we need 240 in order to run heavy loads. In spite of doing, I mean, that's going to be just the first part of this morning. On the second portion of this morning, what we are going to do is that I'm going to give you a circuit in which is on Iconestoga. On this circuit, I'm going to show you from right now. Okay, I'm sharing on my screen here. What you are going to do on that circuit is that you will go to your course content weekly lesson, and then under week 6, you are going to open. Okay, so you are going to be opening this handout, which is called the broken neutral. Okay, so when you open this handout, then once we are done with the first part of today's lesson, then I want you to test yourself, to test your knowledge, your ability to use Ohm's law, your ability to understand series and parallel circuits and apply that knowledge in order to solve for a broken neutral situation that we are going to cover anyways during this lesson. In spite of doing that, then this is going to be the preliminary introduction in order to be able to move into something which is going to be a little bit more advanced, in which we are going to be adding to a circuit, we are going to be adding resistance because all wires have resistance. And then we are going to see that the thing or the thing that determines the amount of resistivity that we have in a wire is based on the length of the wire, the temperature, the ambient temperature in which the wire is. Also, that's going to be determined by the type of material, okay, that we are using for our wire. So it's going to be it's going to be determined by those factors. And this is going to be the introduction into getting, I mean, we are going to do a little calculation here with this simulation, and then that's going to be the introduction into getting into voltage drop, and then we are going to cover all those things like circular mills. And also, we are going to calculate voltage drop using the formula, the formula that I'm going to give you this morning. And I know that you have used, probably you already used in code, another formula, which is in table D3 and table D4. But now we are going to see voltage drop from the theoretical point of view. Now you are going to be able to see how is it that they were able to get to those conclusions that we have in table D3 and table D4 in the code book. Okay, so without further ado, so let's delve into it.
Will this all be on the test on Friday?
Today's topic, yes, it's gonna be part of the test Friday. So Friday's test, I posted an announcement. That's a great question. So there's an announcement here that was posted right here for test number 3. That is going to be happening March 5th, of course. The topics will be work, power, energy, circular mills, and voltage drop. That's going to be our topic. So it's going to require you to spend some quality time going through the material. Okay, so as I have said many times, this is an 8-hour course, and we are only doing 3 hours a week with me. Okay, so the rest of the time is completely up to you. So you have to do your part. So let's keep going then. This is the announcement, and these are the topics: work, power, energy, circular mills, and voltage drop. Those are going to be the 5 different topics that are going to be covered in our next test. And still, it's going to be open all day long. Okay, so let's get moving then, guys. Let's get back into power sources. Okay, two-wire power source. Now, when we have a two-wire power source, the reason to that is because that way we can operate equipment that uses a lot of current. If I were trying to use, or if I were trying to run a load like this one, like okay, so in this case, you can see that it's a 10 ohms load. And in reality, like if we have 10 ohms on this resistor, it is a 10 ohm resistor, but depending on the amount of voltage that we apply to that resistor, we are going to have either more or less current. If this resistor was rated for 120 volts, and we apply 120 volts to that resistor, then that resistor that I'm going to suppose is a heating element would draw a current of 12 amps, and then it would have a watt rating of 1440. Okay, so that's the case at 120 volt. Now, the same resistor, if the same resistor is rated for 240 volts, and in this case, I'm going to use red, and on the other side, then you are going to see something which is very interesting here. Indeed, yes, we are going to have our 240 volts divided by 10, which is going to give us 24 amps. Now, when we have our 24 amps and we multiply the 24 by 240, in order to obtain all power, you can see that the actual power rating of that resistor would be 5,760 watts. Okay, so that being said, the importance of being able to have 240 for heavy loads rather than 120 is that we will be able to use, or we will be able to have a higher amount of output power with a significant amount of less current. And you may wonder, okay, how is it, or how are you telling me with a significant amount of less current? Okay, so on the flip side, like if I were trying to run this amount of wattage, if I wanted to have this amount of wattage from the circuit, and I am going to use only 120 volts, how many amps would that require? Then I would take my 5,760 watt divided by 120 volts, and that would require 48 amps in the circuit. And having 48 amps instead of 24 to have the same amount of power, that would translate into having a way thicker wire. Okay, like this wire would need to be way thicker, like a bigger gauge wire. And also the overcurrent devices would need to be way bigger. So we would need to have like overcurrent devices that are like rated in this case as 60 amps, rather than having an overcurrent device like in this case, which is going to be rated at 30 amps. Can you see the difference there between these two different voltages? Like still the same resistor, but being able to operate the resistor at 240 rather than 120 is going to save us a lot of money. Plus, we are going to be able to have way more power output. Any questions about that? So far, so good. Okay, now that we have established the idea that it's important to be able to have, 240 volts for heavy loads, like in the case of dryers, like in the case of residential dryers, the range, ovens, things like that, you know, like electric furnace, hot water tank, if they are electric, like all these heavy loads that require a lot of watts output, that require to produce a lot of heat, they are better off using 240 volts than using 120. And I already told you why. Smaller overcurrent devices and smaller wires because of that. Now, however, for all the other loads around the house, like toasters, like light bulbs, TVs, everything else, because they don't use as much current, then we use 120 because we are more, we are more directly in contact with those devices. We are always turning on switches and we are always plugging in things around our house. And we use 120 because it is a safer voltage level in case we get in contact, with the appliance that we are trying to operate. Now, having 120 volts in residential is very important. And here we are going to see in the simulation that if we have balanced loads, in this instance, we have two power sources. Of course, in the house, we have AC, but we are not going to cover AC in this course. The only difference between this being DC and the AC source that we have in the house is that the AC would be revolving at an interval of 60 times per second, while this DC system is just two power sources, which is like two batteries that are connected in additive polarity. And if you wonder, so what is that thing that you were talking about with additive polarity? You can see that this negative terminal is connected to the positive terminal of this other power source. So if we call this battery B1, I'm gonna call this one like this, just B1, voltage 1, and this we call V2. When they are connected, negative to positive, like in this fashion, then we are going to have what is called additive polarity, and their voltages are going to add up. By the same token, right in the center here, between the two power sources, we have connected another conductor, which is going to behave as a neutral conductor. I want you to notice that in residential also, this other conductor here is also called the grounded conductor, because right at the panel, this conductor, which is the white conductor, is connected at the same potential of the grounding conductor. Okay, so let's keep moving. Now, if we have, as I said before, a balanced load, then you can see the way that these blue dots that represent the currents are moving through the circuit. So right now, what type of circuit do we have? Do you mind sharing what you think? What type of circuit do we have right now?
Combination.
Okay, so somebody said the combination. So look at the current flow and tell me, how is the current flowing?
Series.
I didn't hear you well, sorry.
Sorry, it'd be a series now,
Series
the way it's
circuit.
flowing.
Yeah, it's just a series circuit. So perfect. It's behaving as a series circuit because we have balanced loads. Now, if these loads, and in this case, I'm using these two sliders on the side in order to be able to fluctuate the resistance on my wires. And of course, like in this case, what I'm going to do is that for this one, I am going to, right here, I have 8 amps. And right here, I have 8 amps. And this is a series circuit. We already said, if we take 15 ohms plus 15 ohms, that's going to be equal to 30 ohms. And having 30 ohms as our total resistance, we have 30 ohms. And if we divide the 240 volts that is being applied to those two resistors together that are connected in series, indeed, we are going to have, as indicated by this current source, 8 amps. And we are going to have 8 amps on both wires. So we have an input and a return path, which is the output, right? Now, if we create an unbalanced load in such a way that we have more current, and what I'm going to do, I'm going to reduce first the resistance on this wire. And I'm gonna go from 10, I want you to look at this resistor here. I'm gonna go from 15 to 10 ohms. Now that I have 10 ohms, you can see that the total current that starts to flow through the circuit is gonna be, okay, it's gonna be like 12 amps. That's gonna be my total current. And through this resistor, I have a flow of how many amps? 12. 12 amps flow through this resistor. Okay. So how do I know that? Well, we are using Ohm's law. So if we have 120 volts, remember that this is going to be the reference conductor, because this wire, this resistor is connected between line 1 on the top here and the neutral conductor. That again is called the identified conductor because it always has some current flowing through it, because we never accomplish perfectly balanced loads. Now that we can see that we have 12 amps flowing through the circuit, and we have 8 amps flowing through that resistor here, so the amount of current that is going to flow through the neutral is going to be the unbalanced load, which in other words is going to be our 12 minus 8. So we have 12 amps here. How do we know that? Well, that's 10 ohms. So we have 120 divided by 10 ohms is 12 amps. So here also we have an applied voltage, which is equal to 120 volts. So 120 divided by 15, we already determined before that that was going to be equal to 8 amps. And now that we have 12 here and 8 here, we have an unbalanced current, unbalanced load, and that unbalanced load current is going to go through the neutral conductor in order to complete the circuit. By all means, if I were able to rebalance our loads, then you can see once more that the amount of current that we have in the neutral is going to be 0. Any questions about that? So I posted this link on Iconestoga because I want you to be able to play with this. I want you to be able to change the amount of resistance that we have in the wires. The amount of resistance that we have for each individual load. And by changing that individual resistance, you are going to be able to manipulate how many amps are flowing in the circuit. Now,
Okay, so that,
pardon me?
sorry, that right there, we have 3 amps at the top now, going to the 40.
Yeah, because you have 120 divided by 40.
So how are you getting
have-
12 down below if you don't have 12 going in?
Oh, so you have
coming-
120. Okay, so we're using Ohm's law here, right? The voltage between these 2 points here is 120 volts. So 120 divided by 10 ohms is equal to 12 amps.
Okay, so the current is coming from the neutral there then? Is that where it's getting the
That's how
power
it's
from?
flowing. Yeah, that's how it's flowing.
So it flows both ways along the neutral?
Pardon? Yeah, it's got to be flowing either way, depending on what is the amount of load that you have in the circuit.
Okay, thanks.
You're welcome. And that's why it's not called a neutral. That's why it's called identify conductor. It makes sense now, the word identify rather than just neutral. I mean, that's how it's called in the code book. I hope that you already covered that in code.
Yeah, we had but I wasn't aware that it can go both ways.
Okay. Yeah. So anyways, in this instance that we can see in here, we are using the reason why this is flowing like this, the way you see it, I was able to set up the system to use the electron flow theory. You can see that everything is flowing from negative to positive. And these having 12 amps are coming from here, okay? And what's happening is that you have your 12 amps on this load minus the 3 amps on this load. So the amount of imbalanced load is going to be equal to your 9 amps that you have right on this load here. So let's get moving then, guys. So what I would like you to do, and something that I want you to be aware of, is that even when I has been playing with all these different values here, I provided these 2 sliders so you can see the benefit of having the unbalanced load, or not the benefit of what's going to happen, like when we have an unbalanced load. That's what I mean. Okay, I want you also to notice then what's going to happen when I close this switch. As soon as I close that switch, of course, we are going to have 240 volts applied to this load, which is going to be one of those heavy loads that we were talking about. And then the total current that we have in the circuit is going to be 24 amps that we have for this load. Okay, so we have 24 amps here, and plus the 12 amps that we have from before, plus the 12 amps that we have from before here. So that's why that we have all 24 plus 12, and then that's why we have our 36 amps. Because every time that we closed, or every time that we engage a new load, our current will go up. Any questions, or we are good? Okay, so something that I want you to be aware of is the following. If these were loads based on wattage, okay, I'm going to show you that from Iconestoga. On this little problem that we have in here, now we have the same scenario. But in this instance, we have a 700 watt toaster. Okay, so let's suppose that for a moment that this is not broken here. This is just a regular rounded conductor. It's in perfect condition. And well, we have a 700 watt toaster here, which is connected, of course, to line 1 in neutral. So this receives 120 volts. By the same token, these two other loads that are connected to the other phase, to line 2, we have a 60 watt light bulb and a 10 watt radio. Both of them also have 120 volts. This is getting line 1 and this one is getting line 2. Whatever is going to be flowing through this neutral conductor is going to be the unbalanced load, the difference between the current which is being used between these different components. Now, one thing, one factor, one value that will never change inside these devices will be resistance. Okay. So resistance will not change. So if I were going to lose the neutral, the departing point to determine what's going to be the behavior of these devices on the initial resistance that they have. This is rated, like this toaster is rated for 700 watts. If I were going to use, remember that formula that says that P is equal, so we have 3 different formulas for power. P is equal to E times I. Also that P is equal to I squared R. And also we have that P is equal to E squared divided by R. Okay. Now, we want to determine R, right? Right here, this is the value that I want to determine, and I already told you why. We want to determine R on these loads because that's an unchangeable value. That value doesn't change. So we'll say that R for the toaster, it's equal to E squared divided by P. I'm going to delete these values here, or these formulas. It makes sense. All I did was to swap these two values. I send R to the position of P, and then I send P to the position of R. That's how you do, you can transpose that formula rather quickly. Now that we have, okay, I'm going to do the first, and I'm going to ask you to do the other two. Okay, now that we have, okay, our E is 120 volts divided by the wattage, which is 700 watts. That's going to be equal to 20 point, okay, so the value for that meter, please keep in mind that this light bulb is connected to 120 volts. You can see that the connection is between line 2 and neutral. That's their connection points. So how many amps we have here? 60 watts. 60 watts are being dissipated and 120 volts is being applied. Same thing for the radio. I'm still waiting.
0.5 amps at that light bulb with 240 ohms resistance.
That's good. So we have like here 240 ohms. So I'm going to be writing here the ohmic value because that's the value that doesn't change. 240 ohms. And for the radio, you said it was 1440? 1440 ohms. Perfect. For the toaster on the top, it was 20.57 ohms. That's the ohmic value. I wrote it on amps, but that was an error. So this 20.57 ohms. And now with this information available, we can apply Ohm's law and final currents. E divided by R, E by R, okay? So for this one here, we have our 5.83 amps, okay? And then that's the amount of current that we have on the toaster. And then you said that here we have 0.5 amps. And how many amps on the radio?
0.08.
Yeah, 0.08, which is 83 milliamps. But I'm gonna write it down as 0.083. Okay, so would you be able to determine how many amps we have right here on the neutral conductor?
Zero.
Okay, so keep in mind that these are not balanced loads. Can you see that? They are not balanced loads.
Would it be 5.247?
Yeah, so it's gonna be the amount of current that we have, the 5.83 minus the 0.5 plus the 0.083. So the total amount of current that we have on line two current here is gonna be our 0.083 amps plus the 0.5. That is, the amount of current here is 0.583 amps. That's how many amps we have on line two. But you can see that we have an unbalanced load. How much current we got through the neutral is going to be our 5.83 minus the 0.583. That's what it is, 5.247 amps. That's the unbalanced load. Now, I'm going to take you back to here, to Falstad. And I want you to observe what's going to happen, like if we have unbalanced loads. In this case, we have an unbalanced load, which is, okay, that is also working. We have an unbalanced load of 4 amps. But if we lose the neutral conductor, then look at what's going to happen. You see how everything becomes awkward? Because now what's happening is that these ohms are going to be adding to these ohms, and the total voltage, which is going to be applied between the two loads, is going to be equal to 240. So we are going to have, in this case, our 240 volts divided by 25 ohms, which is going to give you your 9.6 amps that we have right here on the top and bottom. Under normal conditions, we are going to have 4 amps of unbalanced load, and each device is going to be taking the regular amps, 8 and 12. But under abnormal condition, like when we lose the neutral, then of course, because this is rated, like this one, let's say, it is a device that is rated for 8 amps. This device is rated for 12 amps. Am I making sense when I say that this is rated? Okay, I'm just gonna say that this is a value that doesn't change. So this is rated for 8 amps. And this one here is rated for 12 amps. So this one on the top, this one on the top, have a power output, which is going to be equal to 120 volts times 8 amps. So the power output of this component here is 960 watts. And that's before we lose the neutral. While the power output on this one is going to be equal to 1440 to 1.4 kilowatts. But I'm just going to write it down as 1440 watts. Okay, so that's the watt output for both, okay? Now, if we lose the neutral, now, because we are going to have 9 amps flowing through that device, and I'm going to use yellow now just to simulate. So as I was telling you, so in this instance, we have this value, which is the 15 ohms, that is an unchangeable value. The reason why I'm able to manipulate all these values is because I had a variable resistor, because I wanted to be able to manipulate all these values at first. So you can see the unbalanced current through the neutral conductor. Once more, because this value is not going to change on a regular load, then we have 15 ohms, and we have here 10 ohms. But now that we have 9.6 amps flowing through this conductor, we have 9.6 amps. When we multiply this 9.6 amps and we use our formula that say that power is equal to I squared R, we'll be able to determine how much is the power output on that device. So 9.6 squared times the 15 ohms. If this was a light bulb, at this point in time, it would be super bright, because now this is going to achieve a power output which is equal to 1,382, 1.3 kilowatts. While this other device here is going to have a power output, so this power went up. If that was a light bulb, that light bulb would glow super bright. And if that is a heating element, then the heating element is gonna go like super, super hot. It's gonna get red hot, okay? While on this one in here, we have the same 9.6 amps. And if we apply the same formula, and we have 9.6 squared times the 10, then we only have 921 watts. So at the end of the day, what's going to happen in the circuit over time is that this whole circuit is going to collapse, because this one is going to stop working. Okay, like this one is going to stop working here because it's overheating, and because it's a series circuit, the whole system will collapse. Now, if we go back into the initial circuit that we were doing, where we found all these different values, what I want you to do next, now that I show you already what's going to happen with the simulation, what I want you to do next is that I want you to determine what's going to happen when the neutral breaks down. We already saw which are going to be the normal current levels. We saw how many amps we have here, like the 5.83, but here we have the 0.8 amps. We also saw the unbalanced load, and we also saw how many amps we have on each individual component. At the same time, I already mentioned, and we already determined, that this value of R doesn't change for either the toaster, the light bulb, and the radio. Those are the fixed values. the fixed unchangeable values. So I'm gonna give you like from now until 9, so take 6 minutes, and then we are gonna take the break, which is gonna be 10 minutes. And I just want you to look at this problem. And when we come back from this problem, that's when we are gonna be starting, or we are gonna start getting into voltage drop. Okay, any questions?
Sorry, how long are we working on this for?
So I'm gonna give you 6 minutes to do this.
Okay.
And then you take your 10 minutes break. And do you understand what I want you to do?
It's just
So-
double the voltage, right?
Yeah, perfect. So you are going to calculate the EMF, the amount of voltage that you are going to have, like once we lose the neutral. Right now, when the neutral is working, they have 120 volts. But what if we lose the neutral? Then how many volts each one of these components are going to be getting? And also, I'm going to add something more in here. I want you please to determine the amount of power that each one of these devices will get if, if the neutral breaks down. Will this light bulb will glow brighter? Will the toaster be like red hot? Or the radio, will it work or will it burn out? So I want you to find that, and then, well, the time is yours. Okay, guys, so now to keep going, what we are going to do next is that we are going to simulate the following now. Under the same simulation, I'm going to be adding 2 small resistors here. I'm going to be adding 1 resistor to this line. So let me do that pretty quickly, and also to this other line in here.
Gregory,
And
we're
the
going to go
point
through
of
the
adding these
answers. Sorry.
resistors to these 2 lines is because all wires have an amount of resistivity. They have a wire resistance, and that wire resistance is going to cause a voltage drop on the wires, and it's going to cause what is called an I squared R loss. And that's why I'm going to be adding, okay, in order to determine the I squared R loss, that's why I'm going to be adding
Hey, Gregorio, sorry. Are we able to go over that
those
question?
2
Make sure-
resistors.
Hello?
Can you hear us?
Okay, somebody asked me just to go over the question. Sure,
Yeah.
we can do that. So there's, thanks for asking. So then let's do this. Let's go back to the other question then, to the question that I gave you before the break. So we are back in here. Okay, so far, what do you want to know about this circuit? So far, you were able to calculate all the different values. So is there anything that is not clear about the values that you obtain from this circuit? Like, would someone care to share once we lose the neutral and we have this broken neutral? Would anybody care to share, like, how much was the voltage drop that we have on the toaster and how many watts the toaster is producing, and also the voltage drop that you found for both of these components? I'm just asking that because that way we don't have to go again through the whole calculation process, even when I could probably just be quiet and do it within a couple minutes. I want to be able to get you engaged in what we are doing here in this class. So can anybody type what they got for the voltage drop here? Remember
got
that I told you that
0.
resistance doesn't change. That's the value that is unchangeable because it's a fixed resistive value.
I got 21.8.
For watts or volts, or is that for the toaster?
Yeah, the voltage drop for the toaster.
See, I got a lot less. I got 0.14 amps total.
I'd like
And
to
it-
see it done if that's possible. I just, I'm not sure if what I did was correct.
Yeah, I'm way
so-
off then. I got 1 amp for the 1.06 amps for the whole circuit.
Okay, I did 1700 ohm at 240 volt.
Okay, so let's check. Just give me 1 second, please.
Yeah, I got 220 some. Oh.
Okay, so let's do the following. So we'll go back. Okay, so let me see. Somebody is writing something down.
I treat it as a 240 series volt circuit. Don't know if that's right, but that's how I did it.
Yeah, so the circuit becomes a 240 volt, but not a combination. It becomes just a series circuit. Well, yes, a combination circuit. It becomes just a regular combination circuit where this device is connected in series with these two other components that are connected in parallel. And that's essentially what it becomes. So let's go over this very quickly, okay? That's fine. So at least because I don't have all this information like written on the screen, at least you can tell me how much it was the value. Like I remember this one to be 240 ohms.
Yeah.
Okay, I'm not gonna write the 0.5s that we had before because now we are going to assume that we had a broken neutral. And this other one here, it was 1440 or something like that. Remember how much it was? How many ohms was this one?
1440.
1445.7.
I know where I went wrong. I treated it as series. I forgot those two were in parallel.
Yeah, that was 1440 ohms, 1440 ohms. That was the radio, and that doesn't change. Okay, so now the amount of resistance that we have on the toaster was 20.57, as far as I can recall.
Yeah,
20.6.
Okay, so this one was 20.57. And yes, indeed, this becomes a combination circuit. In other words, you could see it like this. You could say, well, here I have a resistor, resistive load, which is equal to 20.57 ohms, which is connected in parallel. This other line that I just draw is this one that we have here at the bottom. That is connected in parallel with two other resistor, one that is equal to 240, this one here, and the other one which is worth 1440. So in order to determine how much is the total voltage drop that we have on each individual component, first we have to solve for these two parallel resistors. 240, when we are going to use the product over the sum, so we are going to say 240 ohms times 1440 divided by 240 plus 1440, or you can use the reciprocal formula plus 1440. Okay, so that's going to give me the total ohmic value for these two branches. Myself, when I do the calculation, I get 205.71 ohms. That's the ohmic value for these two together. So I am getting 205.71. And now that we have 205.71 ohms for these two resistors, or these two loads, then we add the other ohmic value, which is the 20.57. So the total ohmic value for the circuit is going to be equal to 226. Okay, so between these 2 points here, between here and here, we have an ohmic value which is equal to 226.28 ohms. Now that we know the total ohmic value, we just take our 240 volts, which is going to be the applied voltage with the broken neutral, and that's going to give me 1.06 amps. Any questions so far? Any questions, or we are good? Can we keep moving?
Yeah, I'm good.
So with the broken neutral, we know that we have 1.06 amps here now. And if we know how many amps we have, because we also have the amount of the ohmic value for this toaster, which is 20.57, once more, we are going to use the formula that says that, okay, so we are going to use the Powell formula. Power is equal to I squared R. And that's going to give us the power output. Also, we can use the formula that says that in order to determine voltage is equal to I times R. Okay, so that being done, so we are going to have our 1.06 square times the 20.57, and that's going to be equal to only 23 watts. I'm just going to round it off. 23 watts output only. And the voltage drop that we have on this toaster now is going to be equal to our 20.57 times the current, which is 1.06. So we only have here 21.8 volts. Any questions? Now, on the flip side, All we have to do left is just to take our 240 volts. So again, like we have here between these 2 points here, and the bottom here, we have 240 volts. So we already know how much is the voltage drawn for this component, which is 21.8. So 240 volts, which is the total minus the 21.8, is going to be the voltage drop that we have on these two other components that are connected in parallel. That will be 218 volts to 18.2. That's going to be the voltage drop that we have on each individual component. So what that high voltage is going to translate into this light bulb becoming super bright, because now instead of having 120 volt applied to it, now we have 218 volts applied to it. While the filament of the light bulb, if that was an incandescent load, while the filament of the light bulb is good, then the light bulb is just gonna glow super bright and then it's gonna burn out. So how much would be the power output? Well, we got a voltage, and when we divide that voltage, when we multiply that voltage, we will have to multiply times the current, but I'm just gonna use once more to determine that power, I squared R. Okay, to determine the power, I could use I squared R, or I'm just gonna go back and say that power is equal to E squared divided by R. That's gonna be the straightforward formula without having to do a lot of calculations. So on the 60 watt light bulb, we are going to have 198. So here we'll have 198 watts output. 198, that's a lot of wattage. Like 3 times the amount of watt that we used to have. So that light bulb will surely burn. And the amount of watt output that we would have in there, it would be 33 watts on this one. Well, of course, the radio won't be able to do that, so it will just burn out right away. Now, how much is going to be the current? We have 198 watts. We can do this different ways. We can take the 198 watts and divide it into the voltage in order to determine current. We could also use Ohm's law here and say voltage divided by R. So I'm just going to use voltage divided by R, which is my 218.2 divided by my 240. So on this one, I'm going to have 0.9 amps. Well, 909, I'm going to write all the values. While on this one here, same thing. It's going to be our 218.2 volts divided by the resistance, which is 1440. So that's going to give me 0.151 amps. And of course, this value, this amps value plus this amps value has to equal 1.06. So very close at least. And actually my calculator, when I do the calculation, I get a very, very close value. I get 1.051 because of some of the decimals that will not include it in the calculation. So gonna make sense now that I explain all the steps?
Yeah, thank you.
I can, let me see.
Yeah.
Like, okay. Perfect. Okay. You're welcome. So let's keep moving, guys. So what I wanted to show you before I got into explaining this problem, and the reason why we are doing this problem, and the reason why this is on that little green book, is because we want to make you aware on why is it that we use systems like with 240 volts, like why we use 240 volts. And you may wonder about why do you use 240 volts even when if we lose the neutral, then it's going to be a complication. Well, actually, the good news is that if you happen to lose the neutral right at the transformer for some odd reason, and your neutral conductor is grounded, then this is not going to happen. If you had a grounding connection, if your neutral is properly grounded, even if you lose the neutral at the transformer, the grounded or the bonding to that neutral is going to serve as your returning path. And this is not going to happen in the circuit. Okay, so now let's move back to Falstadt, and let's get into the other part of this voltage drop. Before I start explaining the last circuit, what I was telling you about is that each wire, there's no a single wire that we use in the field that doesn't have its own resistance. All wires have resistance. What I'm going to do here is that I'm going to be adding pretty quickly a little resistor to each one of, and this little resistor that I'm going to be adding is just to simulate the resistance that we have in the wires, okay? So that's why I'm going to leave it rather small. We are going to say, just like in the book that you have, that this resistance is equal to 0.2 ohms or 200 milliohms. Also, something else that I want to do is that I'm going to be adding a voltmeter right on the top here. Because, and you may wonder, why a voltmeter on a wire? Well, because through the length of the wire, you are going to experience a voltage drop. You are going to have an actual voltage drop. So the amount of voltage drop through this component is equal to 1.5 or 1.558, we could say, volts. So that's the voltage drop through this length of the wire. So I'm going to be doing the same at the bottom here. So you can see that, of course, because they have the same amount of resistance on both wires, we are going to have the same amount of voltage drop. But something that I want you to notice, is this current. Right now, okay, so we are going to do the following simulation here as well. I'm gonna simulate that this wire goes from 0 to a max of 3 ohms. So you can see what's gonna happen in the circuit. And we are gonna call this wire 1, okay, which is right here. So right now I'm gonna simulate that we don't have any resistance in the wire. We had a perfect conductor. And we are gonna call to this one wire 2 or line 2. Okay, wire 2 and wire 1. So I want you to observe right here, and that seems to have like some milliohms, 30 milliohms. So give me 1 second here to see what's happening to this guy. I doesn't want to go with 0. He doesn't like it. Let me see if I can. At least I was able to do 30. 30 milli. Let me see if I can go something smaller than this. Maybe 10. We'll take 10. Okay, I think that's the minimum that I can get, 1 milliohm. But having 1 milliohm, you can see here that pretty much we don't have any resistance in the wire. So if you do our 120, or okay, so if we do like 15 plus 15, which is our 30 ohms, and we do our 240 divided by 30, it's gonna give you the 8 amps, right? Because we had a balanced load. Now, what I want to simulate here is the following. What's gonna happen when we have wire resistance? In this case, I am going to increase, and I want you to see what happened right on the top here. I want you to notice what happened to this wire, and I want you to notice as well what's going to happen to the total current that we have in the circuit. So as soon as the amount of resistance goes up in my wire, and I'm just going to simulate the same thing that we have in the book. And let's say that now we have, well, I was able to get it to 210. Okay, so I'm gonna leave it like that, 180 milliohms. If I only have 180 milliohms of resistance along the length of the wire, we are going to experience on the wire itself a voltage drop of 1.4 volts. Because we always have an input and an output, because we always have that, then of course, the amount of voltage drop that we have on one wire is going to be multiplied times 2. And we'll get to that in just a bit, because we always need to have a return wire. So because of all the wires, they are contained within a cable or a conduit. So if I'm going to be feeding this circuit, both the line 1 and the neutral, they got to have the same length. Now, the 3 factors that are going to determine this voltage here, that's going to be determined, I said at the beginning, by 3 things. One of them is called gauge, And the gauge in your code book is given in American wire gauge, AWG. And also after the 4-up conductor, right after like the biggest conductor you can get with that designation, AWG, is going to be 4-up. After that, we jump to KZM. And this is a topic that we are going to cover in just a bit. How do we get this value of KZM? Okay, circular mills. Where does that comes from?
Metric system.
The other factor that determines the voltage drop will be the length. Of course, the longer the conductor, the more resistivity that the conductor is going to have. The other factor that is going to determine that resistance that we have in the wire will be the type of conductor, in other words, the material. For example, you can see that we cover in theory that, for example, aluminum have 3 valence electrons, while copper only have 1 valence electron. If you went to table 1 to 4 in the code book, you would see that the minimum aluminum conductor size that we can use as per table 1 to 4 in the code book is going to be a number 12. That's going to be a number 12. And at 60, with an insulation rating of 60 Celsius. While copper, the minimum size conductor that we can use as per those tables is going to be a number 14 at 60 Celsius. And the rating for both conductors is going to be only 15 amps, despite the fact that aluminum is thicker because it's a number 12 than copper. Okay, so the type of material is going to determine how much resistance we have on the wire. And the last factor that we are going to see as well is that temperature plays a role. The temperature, which is the surrounding temperature, the ambient temperature, plays a role on how much we have on the wires. Okay, guys, so
were you just
I left the
talking that whole
circuit
time?
there
We
a
couldn't-
little bit, so you could wonder what's going on. So you could take a look at the circuit and you could start thinking, you know, how this value is going to be affected, like any of these values affecting the voltage drop that you have on the conductor is also going to be affecting your load. And that's why you have to derate the conductors whenever, I mean, because of all these different issues, especially like you use table 5A, which is for temperature. And depending on once you go beyond 30 Celsius, then you have to derate your conductors. Like in today's class, we are going to do all our calculations with a table which is rated at 20 Celsius, which is the standard table which is used in Delmars. Any questions about this portion, or can we move on? Okay, so let's get moving, guys. So listen, if you ask something, it's not that I don't want to hear you. Like, it's something, you know, technology is technology. It's not perfect. So anyways, just type it, okay? If you type, the system always sends me a notification that someone is typing something, okay? So you have a question. Do you have a question?
Yeah, yes, I had the question, and I think the group answered it. So rephrases, as temperature goes up, the resistance goes up.
Yeah, why?
And good question. I don't know.
Yeah, the reason to that is because as temperature goes up, the molecules start moving faster inside the medium. And because the molecules are moving faster, it makes it more difficult for the electrons to be able to flow freely through the conductor.
Right. More energy required to knock them out of their orbit.
Perfect.
Okay, thanks.
Anyways, guys, so let's continue. So what I was telling you now, in the code book, you see that we have up to 4-up American wire gauge, and right after American wire gauge, we have the thing which is called circular mill. So where does that terminology comes from? It comes from the fact that, well, they decided in order to make it easier to make field measurements of the cross-sectional area of a conductor, they decided just to, I mean, like if you say that you have a number 4 conductor or that you have a number 3 conductor, you don't really know what is the thickness of that conductor unless you go to a table and take a look at it. But if you were in the field and you use a caliper and you measure that you have a cross-sectional area in a conductor, which is equal to 1 inch, then you would be able to determine how many circular mills you have in that conductor rather easily. Okay, now let's begin right here on this little circle. When we have a conductor, and this is a conductor, most conductors are round unless we have bus bars. On the conductor, okay, like if we decide to measure the diameter of this conductor, which is represented by the red line up there, if this conductor has 1 inch, if this was 1 inch thick, right? And we take this 1 inch and we divide it in 1,000 equal pieces, then we are going to have, of course, a value which is going to be equal to this, to 0.001 inch. Now, every time then that we have 0.001 inch, we are going to say that we have 1 mil. We took 1 inch, we divided that 1 inch in 1,000 equal pieces. 1 liter portion was 0.001. That was 1 fraction, 1 in 1,000. And 0.001 inch is equal to 1 mil. Now that we have 1 mil, okay, so that's going to be the gauge of my reference conductor. Now, when we take 1 mil, okay, we introduce a new terminology, which is called the mil foot. If we decide to do the following, if we take this 1 mil that we have in this conductor, and now, let's say here, this is just to make a projection for my conductor. This is my conductor. Okay. So I have 1 mil of thickness. That's the gauge. And then the length of this conductor is going to be 1 foot. Now, at 20 Celsius, then I'm going to be having an environment temperature for this mil foot equal to 20 Celsius. Then I'm going to have a constant resistivity for this conductor. For aluminum, it's going to be 17 ohms per mil foot. For copper, it's going to be 10.4 per mil foot. And you may wonder, do I have to memorize okay, these numbers? No, you don't. In order to find out those numbers, you go back to Conestoga, and under week 6, you have a handout which is called under number 5 here, table. Under that table, you have all the different gauges, and then you have the area in circular mills of all your conductor, the diameter in mills, and we already covered what mills means, and how many ohms. Okay, so in this case, this one is per meter. Okay, so this one has how many ohms you are going to have per meter. But we're not concerned about the meters, like this is per 1,000 foot or 100 meters. The one that I was telling you about just now, like that ohms per mil foot is right here at the bottom. This one. Let's explore pretty quickly like different resistivity of material. As I mentioned before, for aluminum at 20 Celsius, the amount of ohms per mil foot is going to be equal to 17 ohms. For copper, I told you was going to be 10.4, but you have a lot of other materials like brass, 42 ohms, gold, 14 ohms. Okay, so if you continue, iron 60, and silver is way better than copper. The resistivity of silver is going to be 9.6 ohms per mil foot. Now, I want you, before we get deeper into this topic, I want you to tell me if this ohms per mil foot makes sense, if you know where that is coming from. I stay quiet to see if someone is going to say something. Nobody want to say anything this time? My speaker is working, I think.
Is that the measurement for a foot, like 1 foot of wire? Is that correct?
1 foot of wire, perfect, with a gauge of 1 mil.
Okay, that's where you get the 1 mil.
Pardon me?
I was wondering where the mil came into the foot. Oh, that makes sense.
Yeah. So the mil is the thickness. And we already determined, or we already said that 1 mil is 1 inch divided in 1,000 equal pieces, right? So it's 1,000 of an inch.
So
That's
this is,
1 mil.
so we're not talking, are we talking actual? It's not millimeters. A mil is different, right?
No, the mil is different. Mil is 1,000 of an inch.
Okay.
Okay,
Thanks.
that's not millimeter. Okay, you're welcome. So now that we know, we are going to be using, like going forward, we are going to be using this table a lot because we'll need to refer to this table in order to determine what's the amount of mil foot that I have in my conductor. Now, let's get back. So we are back here. So now that we know, okay, now that we know like how many ohms we have per mil foot of copper, okay, so we'll jump into the next step, which is called circular mills. Now, let's do the following. Let's do a little play here, okay? If I want to find the area of a circle, I have that the area is equal to r squared times pi, or pi times r squared. And r means the radius of a circle is going to be equal to the diameter divided by 2. Now, if we have, and this is the next step, let's say that we have, okay, an diameter which is equal to 1 mil. That's going to be the diameter of my conductor, 1 mil. Now, if the diameter of my conductor is going to be equal to 1 mil, I can determine how many square meals I have in my actual conductor. All I need to do is just to take my 1 meal divided by 2. Okay, so 1 meal divided by 2, that's going to be equal to 0.5 meals. And that's going to be the radius, 0.5 meals. And then I'm going to use this formula to find the area of my conductor. And you may wonder, why do we need to find the area? And it's because that's how we determine the circular mills that we have in a conductor. We're going to see that in just a moment. So we have that pi is equal to 0.7853 square meals. Are we good so far? That's going to be the area of the conductor, the area of this conductor in square meals. We have 1 meal in diameter. We apply the formula to find the area, and we find that we have 0.7853 square meals. Any questions or doubts about that area? If you don't have any question, let me tell you guys that from here on, every time that we have 0.7853 square meals in a rounded conductor, we are going to say that we have 1 circular meal. And that's where the term circular meals comes from. It comes from there, from the amount of area that you have in a given conductor. So that means that if we have, okay, like let's say 2 circular meals, okay, so that means that we can determine like how many square meals we have in the conductor. Okay, so that would mean that we can determine how many inches we have in the actual conductor. Now, to make things easier, we had a formula that says that the diameter of the conductor in meals, diameter square, is equal to circular meals. And I'm going to show you that in just a minute. Like, let's say that we have another conductor here. We have another conductor here, okay? And this conductor have an area, oh, no, an area, excuse me. It have a diameter, which is equal to 2. Like, this has like 2 meals in diameter. That's the diameter of my conductor. Now, if I have 2 meals and I apply this formula, that means that 2 square is equal to 4 circular meals. So does that mean that if we have a conductor, which is, let's say, okay, like if you look into your code book, probably you can find that 250 kcm, and they used to call it like MCM. Now we call it KCM. It is the same thing. M, it is the Roman numeral for 1,000 mil, while K means it's just the engineering notation for 1,000. So M and K is the same thing. MCM, KCM means the same thing. So does that mean that if we have a conductor that have, let's say, 100 mils in diameter, we have a conductor that have 100 mils in diameter, or, okay, then we can determine like the circular mils, that's gonna be 100 square. And I'm gonna give you another one in just a minute. So that's gonna be 100 square. That's gonna be equal to 10,000 circular mils. Or in other words, you are gonna have 10 kcm. Okay, so now let's suppose that I do a field measurement for a conductor, and that I find that my conductor is 1/4 of an inch thick. Okay, so when I measure between these 2 points on my conductor, I find that I have 1/4 of an inch. 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 1/ That's the thickness of my conductor, 1/4 inch. So that means that I'm gonna have to convert this 1/4 inch into mils to find what is the diameter in mils. I can do a mental conversion. 1/4, that means 1/4 of 1,000. In other words, 250 circular mils, or excuse me, like mils. And if I apply this formula, okay, by saying 250 mils a square, that's going to be equal to 62.5 kcm, kc mils. Any questions about that? We are good so far?
I think so.
You're welcome. Okay, perfect. So let's keep moving, guys. Now, if we were going, just to finish with all this, if we were going to take the 2 mils that I was telling you about in the beginning, let's take these 2 mils and let's find how much is going to be the square area in mils for this new conductor. So we are going to have that's going to be equal to 3.1416 because we are going to have, okay, 1416, okay? So we are going to have what? We are going to have our 2 mils divided by 2. That's going to give you 1. 1 times pi, 1, that is here. 1 square is going to be 1 times pi. That's going to be 3.14 square mils. So if I decide to divide this number, remember that I told you before that every time that we have 0.7853, okay, 0.785, okay, it should be 54. Well, let me see if I did something wrong, times, yeah. So we just round this up to 54, sorry, this one, because the answer is for this, 0.785398. So we just round it up to 0.7854. So every time that we have 0.7854, we are going to have 1 circular mil. So if we find the diameter in mils and we find the area, the square area in mils, if we divide that square area that we have in mils by 0.7854, that's going to give us the amount of circular mils, which in this instance as well is going to be 4 cm, circular mils. I'm just telling you that because you were going to have to go through this handout and do all these conversions. Okay, but please follow always this formula. That d squared is going to be equal to circular mils. Now, let's get moving. Also, we can determine how many circular mils we have in a bus bar, okay? I already told you guys that every time that we have 0.7854 square mils, I already told you that every time we have that quantity, that we have actual 1 circular mil. So now I'm going to give you an example with something else. Let's say that we had a bus bar in this instance. We got a bus bar, and the diameter of this bus bar is 100 mils width by 50 mils. Okay, it's going to be like 100 by 50 mils, okay? So now I can determine from this bus bar my square area by multiplying the length by the width. So I have 100 times 50. That's going to be equal to 5,000 mils. 5,000 square meters. And because I told you that every time that we have 0.7854 square meters, we have 1 circular meters. If we divide this 5,000 square meters into 0.7854, then I will be able to determine how many circular meters I have on my bus bar. In this instance, I have 6,366 circular meters on that bus bar. Any questions about that?
Yeah, what did you just do? Like, why are we times 100 by 50? Because like, isn't it circular?
No, I mean the circular meters, it becomes a unit of measurement in order to determine what's going to be the area of a conductor, either on a circle or on a bus bar.
So you're saying though that like this somehow has told us how to put a circular connector in a rectangular hole or something, like how many we can put in there, or?
No. This is telling you, like, you had a bus bar, let's say, like when you were using like high current, you're not going to be using like the regular, whatever, rounded conductors. Like for some high current, you use, especially like in industrial applications, you are going to see panels that had a bunch of bus bars.
Yeah, I see that, and you've calculated the area of the bus bar, and you
Perfect.
have the area of the KC mill. But what is this telling us?
It is showing you the amount of here is going to be telling you how many circular mills you have in the bus bar. By knowing how many circular mills you have in the bus bar, you are going to be able to determine what's going to be the ampacity of that bus bar, because you're going to be able to equate the amount of the area that you have in a bus bar to the area, I mean, like in a rectangular bus bar, you're going to be able to equate that value to also a rounded conductor. Okay, so to keep it simple, so you see it in perspective, if we have, you see like this little square that we have in here, let's say that this little square is 1 mil in diameter, okay?
Like,
So
I get what you're doing. You're calculating the area, and you're saying how many like cm
circular mills we have in the bus bar.
Yeah, and I did. Okay, great.
And the
done.
reason why
I
you want to know
understand
that, and the reason why you want to know that is because you want to be able to determine what's going to be the gauge of the bus bar. Like if I told you, okay, I have like whatever 5,000 square meters in a bus bar, so what? I mean, how does that translate into a useful number, you know, into something that I can use? Yeah, we all convert in a square meal to circular meals. That is true. That's what we are doing. Okay, so can we keep moving then? Very good. Yeah. Thank you, Pat, for saying that. So we are going to equate the bus bar to a round conductor equivalence. That is true. So do you want to go for a little break, or do you want to keep going? Okay, so 5 minutes break. Sure, we'll take a 5 minutes break, and then we'll come back, and then we are gonna go until 9:50 because you're gonna go to your next class. When you come back, then we are gonna be getting into all this voltage drop and all that stuff. Okay, so please go for a break. I'm gonna be putting the timer for 5 minutes.
Hey, Gregorio, are you gonna upload this this Zoom meeting?
If you want me to, sure, I can upload.
Yeah, because if we have this on the test to be helpful, we'll go through it through the week. If we have
Yeah, that sure. I'll do as soon as I can.
Yeah, thanks.
You're welcome. So just take 5 minutes, guys. I'll see you back at 9:11, 9:12, let's say. I'll put a timer though. Okay, guys, so let's continue. What we are going to do next is that we are going to be doing together a couple of problems like, okay, so in order to get you started with this, and then we are going to be moving on how is it that temperature is going to be affecting the resistance in a conductor. Now, in the very first question that we have in here, we are asked to find the circular meal. Okay, so don't get confused by the word area. We could pretty much get rid of it, but we are just going to be finding the circular meals, the cm of a conductor, if we have a diameter of 102 mils. So we have our conductor here, and then the diameter is 102 mils. So we are just going to follow the formula that I showed you before. So diameter a square is going to be equal to circular meals. So 102 squared, that's going to be a very simple answer. 102 squared is going to be equal to 10.4 kcm, or 10,404. That's going to be the answer for the diameter square. So we are going to square this number, the 102, and we are going to have 10,404, but we never say that we have 10,404 cm. We say that we have 10.4 kcm. Are we okay there? Okay, so let's get moving with the next problem. Now we got to find the diameter of a conductor with a cross-sectional area of 66,370 circular meals. Okay, so we have this many circular meals, and because the formula say that d square is equal to cm, all we have to do is just to transpose. So this exponent is going to go to the other side of the equal sign, performing the inverse operation. In other words, we are going to have that diameter is equal to the square root of cm. And the answer will be equal to 257.62 mils. That's going to be the diameter of our conductor. That's very straightforward. As long as you remember the formula, okay, you'll be okay. I mean, this is very straightforward math. Any questions about that? Now, let's get into something that looks more like that resistivity in the conductors that I was telling you about before. So in this instance, we have what is the circular meal area, the cm. That's what we are trying to determine in a copper conductor that is 1,000 feet long. I want you please to keep in mind that whenever we are using circular meals, if this length had been given to you in meters, and you may wonder, but why meters? Well, because sometimes actually in Canada, we use meters legally it's meter. We use the metric system, but in the field, we tend to use both. We interchange meters and feet, and we use like the two different units, both the international, the metric system and the imperial system. So we have 1,000 feet, which is good because in that case, we don't have to do any conversion. And then we have a K factor of 10.4. And I already showed you where the K factor is coming from. Subject number 5 in your weekly content. And then the resistance of the wire.
Where was the, sorry, where was the K factor? What is the
Oh, okay.
K?
Yeah. So if you remember, 1 second here.
That
So
was
on
the
that
chart you had,
printout-
right?
That printout on that chart, that bottom little chart, that those are all K values.
Yeah. So you'll see it like if I can show you once I finish with this, but if you don't remember, you are going to be able to see it on the video, but I can show you at the end of the class. Okay. So let's keep moving then. Let me see if I have the formula open. No, it's not open. Okay, so it says here that we got to express the answers in circular meals and square meals. Okay, so now let's write a formula. We have that the resistivity of a material, the resistance of a material. Okay, I told you before that the resistance is going to increase if the length increases. Okay. And also, it's going to be depending on the type of material that we have. So L times K divided by circular meals, which is the area, because the thicker the wire, the less resistance that we are going to have, is going to be equal to the resistivity. So, right, like if we have this formula, then we have the following values. We have the value for R, it was given to you here. It says that 1,000 feet long, this 1,000 feet long copper conductor have a resistance, which is equal to 0.1239 ohms. And the K factor is going to be 10.4 because we have copper and it's 1,000 foot long. So we are going to transpose the formula in order to find the thickness, the circular mill area of this conductor. To do that, then we are going to rearrange the formula and we are going to say that Cm is equal to L times K, because all I'm doing, like this Cm, it is dividing, it's going to go to the other side of the equal sign, performing the inverse operation, multiplying. And this R that is multiplying is going to come to the other side of that equal sign, performing the inverse operation, which is dividing. So Cn is equal to L times K divided by R. And when we input all that information in the calculator, then we are going to be able to get our CMs, our circular mills. So the length is 1,000 times our 10.4. And then that's going to be divided by all R, which is 0.1239. The value here, once I input my numbers, and please do it at home as well at the same time, my number here is 83,938. And that's going to be the amount of circular mills that I have. Now, if I want to know, so I'll take you back to the table. If I want to know, so what's going to be the gauge of that wire? I know that you are telling me that I have 83,938 circular mills. So what is the closest wire gauge that we have from the table? If we do that, okay, just give me 1 second here so I can show you that table once more. That's the table. Remember that the value was 83,000, right? So if I want to know what is the closest one to the conductor that I have to employ for that, I mean, what that conductor looks like.
Number 1.
Perfect. It was like every time that I leave the screen, I lose all my information, but it was 83,000 that we had, right? 83,600. So indeed, that's going to be a number 1 conductor.
So Gregorio, our number was 83,900. Are we allowed to round down to number
No,
one?
no, no,
or
no, no,
since
no,
it
no.
was
Oh,
higher?
thank you for letting me know. It was 83,900.
Yeah.
Yeah, so it's the conductor. I mean, it's gonna be close to a number one. However, it's gonna be close to that actual conductor. However, if you were going to use that conductor and you are taking voltage drop and everything else into consideration, you are not allowed to go down. You have to always go up to the next available conductor. Okay, so if I were going to ask you, so what's going to be the conductor that you have to use for this service or this circuit? The answer would be a 1 ohm. Are we clear about that?
Yeah.
Perfect. That's good to know. Now, also it was asking to express this in circular meters, okay, and also in square meters. To express that value in square meters, we just remember what we got to do if we want to express that value in square meters. We just take the circular meters and we multiply by 0.7854. That's all we do. And you may wonder, so why you do that? I told you before that circular meters is equal to square meters divided by 0.7854. So if I am looking for a square meters, if I have circular meters and I am looking for a square meters, then this 0.7854 goes to the other side of the equal sign doing the inverse operation. So now I have circular meters times 0.7854, and that's going to give us the square meters. Okay, so on the next question, and I'm pretty sure that maybe, I don't know if you have done this in code or any other class, probably instrumentation. I'm pretty sure you have done these conversions in instrumentation already. Have you? I mean, like the conversion of temperature. Yeah, so because I don't want to be raining over wet, I just got to make an observation here, okay? Let's say that we need to calculate difference in temperature, like if the temperature increases from 40 to 130 Fahrenheit. Okay, let's do this calculation here. If we have a temperature increase from 40 to 130, and we are going to be using that in order to determine, okay, the delta T, that means temperature changed. So we are going to have initial temperature, okay, T1 minus T2. So we do like 130 minus 40, that's going to give us 90. Okay, so we are going to have 90 Fahrenheit. That was the change in temperature. Like if we go from 130 Fahrenheit to 40, from 40 Fahrenheit to 130 or vice versa, the change in temperature has been 90 Fahrenheit. Are we clear about that? Now, something which is important to know is that if I had to convert between units, let's say, like if I wanted to know, like what's the difference in temperature, and I'm gonna give you like a better example than this. Let me put it this way. Let's say that in Fahrenheit I have 32 Fahrenheit. You know that 32 Fahrenheit is equal to 0 Celsius, right? And we have like 212 Fahrenheit, and that is equal to 100 Celsius. Now, this is 0 Celsius, and this is 100 Celsius. If I want to calculate the difference in temperature, I mean, if something has to go from 32 Fahrenheit to 212 Fahrenheit, the change in temperature would be equal to 180. That would be the change in temperature, 180 Fahrenheit. Now here, of course, we have that the change in temperature is going to be 100 Celsius. Once I perform my equations and I got my result, I can see that 100 Celsius is equal to 180 Fahrenheit. Okay, so just to give you the heads up, that's why you have that 1.8 here. That's what that 1.8 comes from. But what I want to emphasize is, if we have a problem like this, 40 minus 130, and you know that you have 90 Celsius, okay? If you have 90 Fahrenheit, if you gotta convert this 90 Fahrenheit, and you wanna know what was the change in temperature in Celsius, this delta T was equal to 90 Fahrenheit, but now you wanna know, okay, so if the change in temperature in my system was from 40 to 130, how many would that look like in Fahrenheit? Like in Celsius. If you wanna know how it's gonna look like in Celsius, then you take your 90 and you multiply by that 1.8. Okay, like in this case, you divide by 1.8. But you cannot take this 90 and apply this full formula in order to find out, because you can see that it says here, Celsius is equal to Fahrenheit minus 32 divided by 1.8. You cannot do that when you have done a temperature change conversion. You have to eliminate the 32 and just divide my Fahrenheit by 1.8. But that applies when we have made a conversion and we have found what's going to be the temperature variation between an initial condition and the end condition of the temperature that I want to calculate. So I guess you knew that already, but just making that emphasis before we move forward. So what we are
Would you be possible to change it from Celsius first between the 40, turn 40 Fahrenheit into Celsius and 130, and then just do it that way?
That's what you would need to do. Like if you like you would take your 40 Fahrenheit and convert it to Celsius, and your 130 Fahrenheit and convert it to Celsius, and then you do the subtraction between the two. And that way you are going to be getting 50. But if you just do the, if you do the operation of the 40 minus 130, or the 130 minus 40, and you can take your 90 and divide it by 1.8, and that's going to give you your Celsius without having to do so many conversions.
Okay. Thanks.
Okay, so let's get moving then. On the next slide, or it's not a slide, it's a handout. Like in the next handouts, you are given what is called the resistivity that you are going to be getting in a material because of temperature increase. Now there's going to be a new variable that is introduced into the equation, which is called the temperature coefficient. Okay, so let's look at all these different variables. Okay, so that R with the upward arrow means rise in resistance due to temperature. When the temperature goes up, resistance is going to go up. And we already explained why. Molecules are going to be moving faster. Okay, then we have the R sub zero, which is the original resistance of the conductor. And we're going to do a calculation in just a bit. Then we have that temperature coefficient. And you may wonder, how will I be able to find that temperature coefficient? Before I keep moving, I want to take you back to the same table that we saw before. And now, okay, from this table, you can see that here, Okay, like here, this is where you have your millifoots. But here, then you have that little symbol that you see in that formula, which is called, okay, like that symbol is the temperature coefficient. And we are going to be using this column, depending on the material type that we have, in order to determine how much is going to be the change in the value of the resistance because of the change in temperature. So now that you know where that value is coming from, then we have delta T, and we already saw how to solve for delta T, which is the change in temperature. And then we have RT, which is going to be the total resistance. Now, in the formulas that we are given, we have that R increase is going to be proportional to the original resistance times the increased times that coefficient of temperature increase times delta T. So let's say that we have an example, like in this example here, we got the resistance of a copper wire to be at 20 Celsius. It is 200 ohms. What's going to happen if the resistance goes up from 20 Celsius to 80 Celsius?
The resistance will increase.
Perfect, but by how much? Okay, and that's what we are going to determine now. Like the original condition is that we have 200 ohms at 20 Celsius. So how many ohms are we going to have at 80 Celsius? That's why that every time that the temperature goes up, if the temperature goes up, like if the ambient temperature goes up, you apply table 5A. Why? Because the amount of resistance that you have in the wire is going to increase proportionally or proportional to the increase in temperature. So the first thing that we are going to do here then is that RO, which is the original resistance, is going to be 200 ohms. R alpha, which is the coefficient, temperature coefficient, we have to be mindful of the type of conductor that we are using, in this case, copper. So for copper, it's going to be 0.0039 ohms per mil foot. And I already showed you where to get that value from. And then the change in temperature that we already discussed in the previous page, it's going to be like your 80 Celsius minus 20 Celsius, which is going to be 60. 60 is going to be our change in temperature, okay? Now, it is important to know that in this formula, the change in temperature has to be used in Celsius. If for any reason you got a question where the temperature has been given to you in Fahrenheit, you have to change it back to Celsius. And that's an easy one because here in Canada, we use Celsius for the everyday temperature that we read on the thermometer. Okay, so now, the change in resistance. Okay, so let's see how much the resistance is going to change. So we are going to use the formula, substitute in the formula. So 200 times that 0.0039 times the 60. And that's going to give us 46.8 ohms. So that's how much. This is how much the resistance increased by going from 20 to 80 Celsius. And by the fact that we have a copper wire, okay? That's how much was the increase. Now that we know that how much was the increase, we are going to apply the second tier, the second part of this formula. The new total resistance is going to be equal to the 200 ohms, which is the original resistance, plus the 46.8, which is the increase in resistance because of temperature. So at 80 Celsius, the wire will have a temperature, which, a resistance, which is going to be equal to 246.8 ohms. Any questions about that?
No.
No question. So anyways, like you can always go back to this page, which is in your on Iconestoga. And then what we are going to do next is that we are going to take a couple of problems from Iconestoga itself. So let me get back to Iconestoga. So this one that says resistance of wire temperatures, where the handout, that's the one that we just did. Okay. And now what we are going to do is that we are going to apply the knowledge that we already have into one of the problems. Like there's a lot of questions here. You don't have to do each individual question. Just look at them and do whichever question, I mean, do every other question or something like that, okay? Don't try to do all of them because that would be too much work and it would be a little bit too much. As long as you can do a couple of problems of finding how much resistance you have in a wire, what's going to happen if I change the temperature. If you do a couple of problems of each, then you are going to have a good idea. Even when my teacher used to say when I was in high school that math doesn't enter by the brain, it enters by the fingers. And I have found in my life that that is true. We have to practice a lot to get good at it. So let's keep moving. So in this instance, let's say the following. Let's do problem number 4 in this case. And we are going to determine, actually, instead of 4, let's go to this one, number 5. So we want to determine in this case what's going to be the AWG wire that is required for an application. A couple of conductors are required for running 2.4 mile long power line. The total resistance of the power line is not to exceed 5.6 ohms. And why we don't want to exceed a certain amount of ohms? Because we are limited by the amount of voltage drop that we can have in our lines. So, and then we want to determine in this instance the minimum sized aluminum conductor required for the installation. So let's get into the formula. We know that R is equal to L times K divided by Cm. The thing that we don't know is the Cm. That's what we want to determine. And you may say, well, but it's not asking for CM, it's asking for American wire gauge, and that is totally true. And we'll get back to the table so you can see how we can compare CN to American wire gauge, the conversion of that. Now, we already did a problem similar to this. Now we are doing another one. So the length is 2.4 miles. So we got to convert the 2.4 miles to feet. So we have 1,600 meters in a mile. So I'm just, and my recommendation would be just use Google, and just type convert. Okay, in this case, miles to feet. So if we have 2.6 miles, 2.4 miles, that's going to be equal to 12,672 foot as per Google. Okay, 12,672. Now, you see there that it says a couple of conductors. Okay, so the 2.4 mile long power line, the distance from the substation, okay, or from the generating station to the substation is going to be 2.4 miles. So when we finish, or if we determine the resistance of this wire, that's going to be the resistance for just one conductor. Okay, so it is important, guys, that we multiply everything times 2. So I can right from the beginning say 2 times L times K. And I already explained to you where the 2 is coming from. It's coming from the fact that my connection, if I have a wire 2.4 miles going this way, I gotta have a second wire that is coming in the opposite direction. Otherwise, there's not gonna be any flow of anything.
But wouldn't the size of the wires be the same? So why would you multiply it by 2?
That's a great question. Yeah, you are right. You are right. I got lost for a second here. So we are looking for the American wire gauge. My mind sometimes plays tricks on me. Yeah. So like in this case, because we are looking for the American wire gauge, it's going to be the same. But if we were looking for the total resistance of the wire, then I mean, like if we were looking for the voltage drop, it's just that I got ahead of myself, then we would need that too. Anyways, so let's keep moving. You're all completely right. My mind playing tricks on me. Okay, so we have the 12,672, and then we are going to multiply by aluminum, which is 17, the K factor, and then we are going to divide by the amount of resistance max that we can have in the conductor. So, which in this case is going to be 5.6 ohms. So something important here, okay? The total resistance of the power line is not to exceed 5.6 ohms. The question doesn't specify if it's going to be 5.6 ohms per conductor or if it's going to be 5.6 ohms total. Now, keep in mind that if we have 5.6 ohms of resistance and we multiply, let's say, like if we had a current flow through that wire, which is 100 amps, then we are losing already 560 volts drop on the line. So I'm going to make the assumption that it's going to be 5.6 ohms per both conductors, per the line. Kind of make sense?
So each individual conductor is going to be 5.6 unless
like if we do 5.6 ohms, let's do it that way so I don't get you all confused, okay? So we are going to do like 5.6 ohms here, okay? That's not a problem. Let's do that. And let's determine, let's see how much is going to be the American wire gauge for that. So, well, we have our 12,672, and we multiply by 17 and divided by the 5.6, and that's going to give us 38,468. Okay, so that's going to be the amount of the circular mills, 38,468. So if we go to the table, so as per the table says
4 gauge.
38,468. Okay, so that's going to be, yeah, a number 4 conductor. Now, even when, perfect, thank you so much. So that's going to be number 4. So what I got to tell you about this though, even when it's going to be a number 4 conductor, we got to be pretty careful with this, because if we are thinking about not an isolated conductor, but we are thinking of a power line, a power transmission line, for a single conductor with that amount of resistance is going to be, yes, a number 4. But if the maximum resistance that we have in both conductors, okay, is 5.6, then we would need to divide the 5.6 by 2. Kind of make sense? I'm going to give you an example of that in just a minute. So let me show you another example then. Okay, so let's do a problem like this. Let's do problem number 10. We have a 240 volt, 28 amps, single phase load, 550 from the source. So you can picture what we have. This is my source. And right here, I have my load. My conductor, from here to here, it says a single phase load. So I have a conductor that brings the current, and I have my return. Okay, so that means that I'm going to have 28 amps on both conductors. Now, it's not a secret that we know Ohm's law. And using Ohm's law, we can say that we can determine how much voltage drop we are going to have on the actual conductor. Then, because we are going to be asked to find the voltage drop. So E, which is voltage, is going to be equal to I times R. We are gonna add a sub letter to this E, and we are gonna call it H sub D, voltage drop. ED is equal to I times R. What I? The line current. What R? This R. That says that R is equal to 2, because we got a branch circuit, single phase load, 2 times L times K divided by Cm. Okay? Now that I show you this formula, we can see, and I'm just going to do something quickly here, and I hope that you can follow through. Can you see this R? We said that the voltage drop is equal to I times R. Fair enough? Now, we also said that R, how do we find R? That R is equal to 2. Why the 2? We have a conductor that goes and a conductor that returns. Times L, which is the length, times K, which is the K factor, in this case, copper, divided by the Cm, which is the Silver-Mills. If I wanted to find my voltage drop right off the hop, I can substitute my R by this formula. And then the formula is going to look like this. When I substitute, it's going to look that ED is equal to I, which is current, times, substitute the R for its formula, 2 times L times K divided by Cm. When we rearrange the formula, I always like to call it 2 times Kil divided by Cn.
Hey, Gregorio,
Yes.
would it not work if we just figured out the voltage drop one way and then multiplied it by 2?
Yes, that works. That works. Absolutely, that works. The reason why, like, we do it, the reason why, like, you gotta be careful with that is because when you are looking for the resistivity of the material, or when you are looking for the Silver-Mills of the conductor, then you are gonna have to isolate your formula. You are gonna have to always do your voltage drop first before using the formula.
Gotcha. Okay.
Okay, but then let's get back to the problem, because I just gave you a formula and I explained how I got it, right? So now let's get back to the problem. We want to calculate voltage drop. So let's substitute into this formula. So we have 2, because of the 2 conductors, times K, 10.4, which is the K factor for copper, times the current, which is 28 amps. And I know you almost gotta go, so just give me another minute here, times the length, which is the 550 feet. Now, okay, so we are gonna be taking all that. And then what we want to determine, so do we have the conductor size? Yeah, it's a number 4 American wire gauge. So we have to convert that to circular mills. So a number 4 American wire gauge is equal to, can you please help me there? Okay, like if you have it. So let me see if I still have that open. It's just that if I go back, I'm gonna lose everything that I have on the screen. So
41,740.
Perfect, thank you so much. 41,740. Now, please perform the operation. And the operation says is, let me see what the comment says. 7.67 volts. Sounds about right. And that's gonna be my voltage drop, 7.67 volts. Now that I have my 7.67 volts and I want to know my percentage, because the maximum allowable percentage of voltage drop on any branch circuit as per section 8 in the code book, it's, remember what percentage?
3.
3% max. Perfect. So I take my 7.67 and divide it into 240 and multiply by 100. So I take my 7.67 divided by 240 times 100. So I get like a 3.2% voltage drop, which is a little bit too much. Okay. So that's going to be the voltage drop that I have. The percentage, 7.67 is equal to 3.2%. So that wouldn't pass. So what is the solution? We got to increase the conductor size. And then what you do in that case, if you only want to have a 3% voltage drop, is that you do the same thing. Instead of using 41,740, you use the CMs for a number 3 conductor, and then do the same equation to see what's going to be the percentage of voltage drop that you were going to get in that situation. Anyways, guys, this is it for today. And yes, I'm going to be posting this video for you. And throughout the week, if you have any questions, please let me know. Don't wait until Friday to have questions. And even if you have questions Friday during the test, let me know, okay? So wish you a nice rest of the week.